Hi, ladies and gentlemen. Welcome to Lesson 21. We're post-prog here. We're in the second half of the course, and we're going to start by finishing up Chapter 4. We have 3 more lessons on Chapter 4, and then we'll jump into Chapter 5 before spring break. So today's topic is one of the more important items that we're going to address. Specifically, what we're talking about is the continued look at solving AX equals B. We want to take and solve this equation. However, we're going to look at it a little bit differently than we have been, because this is the situation where we not only have 0 free variables, we have no extra degrees of freedom, but we have an over-constrained situation. And that's really what he's talking about here. He's talking about, and he doesn't say that we're solving AX equals B, but that's really what we're doing, right? So we have AX equals B, and there's no solution. B is not in the column space of A. We have a situation that is over-constrained. And what that leads to then is our desire to approximate the solution, because there isn't an actual solution that's going to solve the system of equations. So it's important to understand how this relates to the other situations that we've looked at. Specifically the operations research situation, where we have free variables, we have an objective function, and we are optimizing things. This is the opposite of that situation. So a couple of notes here. First of all, Strang uses x hat for his solution to the least squares problem. Because we use hat for unit vectors, I am not going to use that notation. I'm going to use x chevron instead. So this is not going to be used, and what I will use instead is the x chevron, so that ax chevron is equal to p, where p is actually the projection of b into the column space of A, and we'll talk more about that. That's going to be the solution to the least squares problem. This whole idea of projections is really important, which is why the material in section 4.2 feeds naturally into our conversation for today. So a couple of things that we will talk about. What we are actually minimizing is this error. And I will show you both as the vector as well as for a line what this error looks like. It's the difference between the actual data and the best approximation that we can come up with. So let me just write this down, right? Our best approximation to the data B is the coefficient matrix times our least squares solution. So the best approximation is ax chevron. That's as well as we can do, and we'll take a look at exactly why that is. And what you notice is this is, as I said earlier, the projection. It's not really surprising that the best approximation we can come up with is the projection of the data into the column space of A. One important note here is the way in which Strang is referencing the material. So he has a few items in here and the way he does the referencing that I don't care for. And so I'm going to use a little bit different notation, but I'll make sure that I make that really clear for you. What he has here, these are the data. So we're typically thinking about data as XY, and however many data points we happen to have. So in this case, we're doing I goes from 1 to M. We have M data points that we're considering, but we're, again, not going to use this XY because Strang doesn't. He uses the T and B. So the independent part of the data is the set of T values, and then the data values themselves are the B values. And the reason we're doing that is because we are building upon this idea of AX equals B, where X is the unknown. So it becomes confusing when we have X as the unknown and X as part of the set of data. So we're going to leave it as the unknown, and then we'll make some modifications to the way that Strang presents the information. All right. So the big point here is, right, what happens when we have no solution? In other words, we have more equations than we have degrees of freedom. And there's no way for us to satisfy all of these equations with the degrees of freedom that we have. So take a read through this material here. He outlines in a good discussion about what it is we are discussing with this particular type of problem. And he gets down to the real solution that we're going to apply, which is this one here. When we have no solution for ax equals b, we're going to left multiply by the transpose. And of course, the ultimate question is, why would we do that? And that's what we're going to talk about today. We're going to address exactly why we want to do that. We're going to start with an example. So he provides example number 1 right here. And he gives us 3 points that do not fall along the same line. And he wants us to approximate this with a line. So you think about linear modeling or regression, those types of things. That's exactly the ideas of what he's talking about here. So unfortunately, he jumps in with this kind of notation here. This is where I'm going to take objection to the way that he's doing this. This is not a good use of notation. The capital letters for C and D are confusing. We use capital letters for matrices. And then the fact that we've got a B, which is the actual data value, set equal to this, the whole thing is confusing. So what we really want to do, and you've seen this before, we have a set of data and we want to model it. We want to come up with a way of taking the inputs and predicting what an appropriate output would be, given that we cannot satisfy all of the data values with our simple model. And we don't want to. We could come up with a model that would satisfy all the data, but it would be overfit. It wouldn't give us the type of information that we want from a model. Simplicity is one of our most important requirements when we're talking about modeling. So in this situation, the model is going to be a line. And the information, the notation that I'm using here is I'm using the x, and we will use these x values, however many we happen to have in our model. Those are the unknown coefficients. So our model is always a linear combination of basis functions. And as a linear combination, we have to have coefficients. Those coefficients are going to be the x variables. And the reason, again, that we're doing that is because it feeds directly into the ax equals b, where the unknown is the x, and the unknown for our model are the coefficients. So then what we want to do, and let me just walk through the steps and make sure that we're very clear about this first example so that you can repeat this and then build up the correct models and the correct set of equations as we practice these problems. So we have the data values. Remember what I told you, the way Strang does the data values is T and B values. For this particular example, we have 3 data values, which he has given to us right here. And those data values are 0, 6, 1, 0, and 2, 0. And what we're going to do is we're going to use our model and we're going to write down 3 equations. Every data point gives us an equation. So f at 0 is going to be equal to 6 is going to be equal to x0 plus x1 multiplied times 0. And this equation just becomes 6 is equal to x0. So the next one, f at 1 is equal to 0 is equal to x0 plus x1 times 1, which gives us 0 is equal to x0 plus x1. And then finally, f at 2 is equal to 0 is equal to x0 plus x1 times 2. And of course, that's going to give us 0 is equal to x0 plus 2x1. It's very easy to see how we can write this system of equations, which is what we have now. We have this system of equations. We're going to write this in matrix vector form. So let me do that. All right, so what we have here are the equations here. And this is called the coefficient matrix. This is our A. This is A times the x vector is equal to B. And that matches up with the type of thing that we have here for the data. We just need to, and this is an area where Strang is really deficient, is in identifying the model. We are modeling, we have t as the independent variable, x coefficients, and that leads to this system of equations written in matrix vector form. There is no solution for this, so we're going to actually solve this using the whole least squares idea, and we'll demonstrate that. But all I need you to see now is this is going to be the type of problem that we run into, where B is not in the column space of A. And so we need to find the best B that we can. And we'll look at how that works in just a second. So minimizing the error, that's where we're going to start. This is how we end up solving these problems. Let me jump forward just a little bit into this really important point here. So what we're doing is we are minimizing this term here. We are taking the difference between AX and B, and we're trying to make that as small as possible. And let me just demonstrate for you what that looks like when we're doing this for our particular problem that we have here. So I have this figure here, which represents the column space of A. So the columns of A are these two green vectors. You've seen this kind of thing in this course before. So these are the two columns of A, and all possible linear combinations of those columns. That's the column space. So the column space is this yellow plane. It is a plane in R3. The black vector is the B vector. So the B vector 6, 0, 0 does not lie inside of the plane, so there is no solution. So what we want to do is we want to find whatever is closest. So let me just demonstrate for you the types of things that we're talking about. Here we have a bunch of guesses of gray vectors that are in the column space of A. And what we want to do is we want to find out which of those vectors in the column space is closest to the vector B. And the difference between each of those gray vectors and the vector B is shown with a magenta vector going from the column space up here. So now the answer to this question is actually quite straightforward. What is going to be the closest vector that exists in the column space? Well, that's easy. It's going to be the projection. It's going to be the vector that I've shown here in blue, which projects B into the column space. And then the red, and we can see the red vector is shorter in magnitude. That's our error vector, and that's what we're measuring, AX minus B. We're looking at the magnitude squared of that. We're trying to minimize it. That is as short as we can possibly get. So the problem that we can now solve is AX equals the blue vector, because we couldn't solve with the black vector, but we can with the blue, and that's the best we can do. That's really the entire idea of what it is that we are doing. We are going to solve this once we have projected the B vector into the column space of A. Let me show you that in a little bit of a different way with our 4 fundamental subspaces graphic. What we have here, very much along the lines of what you already understand, we have our vector, but our vector B is somewhere over here. It has a component. Remember, we have these orthogonal subspaces, our 4 fundamental subspaces. The column space of A and the null space of A transpose are orthogonal to one another. So we have orthogonal complements that make up our B vector. So here's B, and we have this vector here, which is in the column space, and that's really the projection vector. If we project B into the column space, then we're going to end up with the P vector. And then the remaining piece here, this vector, this is the error vector here. And what we want to do is we want to get rid of that piece so that we can solve the problem. How would we do that? We would take the B vector and we would apply, let me shift to the green here, we would apply a transpose. We would map B over to our input side, because when we multiply A transpose times B, we're going to end up eliminating the piece of B that is in the null space of A transpose. And that's really the conversation that he's having here. This is very important. You want to make sure and read through and understand this. This problem does not have a solution. And what he's saying here is we have AX equals B, but the B vector we know is the projection vector plus an error vector. We know because the orthogonal complements between column space and left null space that we can take any B vector that is in the output side and we can break it into these two components. And what's going to end up happening when we apply A transpose, so we take this and we apply A transpose to both sides, and we're going to left multiply by A transpose. We're going to end up with A transpose A X is equal to A transpose the P vector plus the error vector. That's going to be A transpose P plus A transpose E. And the whole reason that this works is because this is 0. So it turns out that A transpose P and A transpose B are equal to one another. They're the same thing. And that's the comment that he's having here, right? We can solve this problem. This is the problem we want to solve. And the way in which we can get there is by applying A transpose to both sides of our equation. Because A transpose applied to B is the same as A transpose applied to the projection. Let me just take this one step further. This is really a key piece of this. Let me again write down, these are called the normal equations. The problem we're going to solve is A transpose A applied to X equals A transpose B. Okay? Knowing that A transpose B is really going to be the same as A transpose applied to just the projection component. But let me further demonstrate how this works. As long as we pick A with linearly independent columns, then A transpose A is invertible. A little bit about A transpose A, it is definitely symmetric, right? It's always symmetric. If the columns of A are linearly independent, A transpose A is invertible. And what that means is that the solution to this is going to be A transpose A inverse A transpose B. And this really now becomes the least squares solution. This is the solution that we're looking for. Let me go with one more step. Let me left multiply by A. That's going to give me A transpose A inverse A transpose B. But the question is, what do you recognize that to be? That's the projection matrix onto the column space of A. So this is really AX, and then what is the projection? This is the projection onto the column space of A for B, but that's just the P vector. So the solution to this problem comes about by projecting B into the column space of A. That's our big takeaway. As he continues on the conversation here, he talks about exactly what I showed you in the MATLAB, but then he's going to look at it from the line standpoint. So he has solved the problem that we were talking about initially, example number 1. And what he's done is he's taking a look at the errors. So what he's done is he's showing us this is what's called a residual. This is the difference between the actual values. So the actual data values are the X's, and then the line is the line that we found when we solved the problem in example number 1. And he gives us the best fit line right here, which again, I'm not a fan of. It's really the model. F of t is equal to 5 minus 3t. That's the model. So if we put in an input value of t, then f of t is the predicted output. The b values are the actual data values. This is where it gets a little bit confusing. So I'm not using his notation. We want to think about this as a modeling problem. So what we've minimized is the difference between the actual data values and our approximation. So let me just highlight this line here. That's the approximation. That's the model. That is the AX chevron. That is the best approximation we can come up with for the data. Now, specifically, of course, it only has 3 points. It has this point here, and this point here, and this point here. What it's minimized is the error. One more time. The error for this problem is AX minus B squared. And what we've done is looked through all the possible x's, like I showed you in the MATLAB, to find the one that minimizes this. From a graphic standpoint, when we square this, what we're doing is we're minimizing the areas of these squares. And I'll show you a better example of that in just a minute. But that's graphically, when we look at this line, that's what we're minimizing. All right, a little bit about the calculus perspective. So a lot of people at this point in the modern technical communities downplay the importance of calculus. That, of course, is a mistake. Calculus is a very important subject, specifically when it comes to optimization. We solve a lot of optimization problems using the ideas associated with calculus. Specifically, what we do is we take a look at the error here, and we end up minimizing this error function with respect to the unknowns. Let me write this out. This is an important thing for me to show you so that you understand. The error is equal to, as we said, AX minus B. And we want to minimize over all possible x's. Well, let's think for a minute about what this is going to look like. Anytime I have a set of equations and they're built upon a model that looks like f of t is equal to x naught plus x1t, that set of equations is always going to be the same. It's going to be 1s multiplied times x naught, and multiplied times x1 are going to be the t values, t1, t2, all the way down to tm. And the set of equations is going to be equal to the data values, b1, b2, all the way down to bm. So when we are looking at this as the problem, which is ax equals b, what we're trying to do then is we are trying to minimize the magnitude of the difference between our best vector on this side and the b vector. Let's take a look at what that actually is. The error vector then is going to be equal to, you recall, this is ax minus b dotted with ax minus b. And what we're going to do is we're going to actually build this up. So this is equal to a times x is going to be x naught times a vector of 1s, which I'm going to designate this way. That's a vector that contains all 1s. That's the first column in A. And then it's going to be plus, right? Matrix vector multiplication is the linear combinations of the columns of A. It's going to be x1 times the t vector. And then it's going to be minus the b vector. And it's going to be dotted with that thing again. Well, that means the error is going to be equal to, and now I need to go through and come up with all of the pieces that are in here. So first of all, we have an x naught squared, 1 dotted with 1. That's going to be this with the first one. This with the second term, this term here, that's going to occur twice. Once there and once here. So we're going to have plus 2, and we're going to have x naught x1, one vector dotted with the t vector. Then we're going to go all the way out to the b, which will be the same as the b with the 1. So we'll have minus 2, we'll have x naught, and we'll have the 1 vector dotted with the b vector. And now we just continue this process on. We're going to have the x1 with itself, and then we're going to have the x1 with the b's. So the x1 with itself is going to be plus x1 squared t vector dotted with itself. And then we're going to have minus 2 x1, the t vector dotted with the b vector. And then finally, we will have plus the b vector dotted with itself. This is the actual algebraic way in which we can calculate for the model that we've chosen. Keep in mind, all of this is predicated on having just a line. We're not talking about other models. We'll talk about that a little bit today, but more next lesson. But this is going to be what the error term actually looks like. Let me rewrite it. All right, so what I've done here is rewritten, and I've actually taken a look at what these dot products are. So 1 dotted with itself is going to be 1 plus 1 plus 1 plus 1 plus 1. We're going to add that up m times because we have m data points. So that's just going to be m. This is going to be the sum of the values in the t vector. This is the sum of the values in the b vector. This is the sum of the values in the t vector squared. This is the sum of the t's times the b's, and this is the sum of the b squareds. So now what he does in this calculus portion is he says, hey, wait a minute, what we want to minimize, of course, is we want to minimize the function e, which we do by taking the partial derivatives and setting them equal to 0. So we're just going to differentiate here. We have 2x naught m plus 2x1 sum of the t sub i's. All the sums go from 1 to m. I just left that off. And then there are no x naughts there, and there are no x naughts there, and we have, so we have x, oh, this x naught term here, sorry. So we have minus 2, the sum of the b sub i's, and then the last 3 terms don't have any x naught in them. So then we have the partial e with respect to x1. We're going to set that equal to 0. That's going to be equal to a 2x naught sum of the t sub i's. The third term doesn't have an x1. The fourth term has a plus 2 x1 and the sum of the t sub I squareds. And then our next term has a minus 2 sum of the t sub I b sub i's. And then that's it. What you'll notice is we can cancel out 2's all the way through. And we can rewrite these because they're equal to 0. We can rewrite these two equations. I'm going to skip that step and jump right into the representation in matrix vector form. So in matrix vector form, what we have is we have x naught x1. That's our vector of unknowns. And then we have the coefficients. So for x naught, we have m. And then for x1 in this first equation, we have the sum of the t sub i's. And then we are going to move this to the other side of the equation. So that's the sum of the b sub i's. In the second equation, we have the sum of the t sub i's. And then this next one, multiply x1 times the sum of the t sub i's squared. And then finally moving that to the right side of the equation, we have the sum of the t sub I, b sub i's. So this is the equation we need to solve for x naught and x1 in order to minimize the error associated with least squares. We're just going to hold on to that for a minute. This is what the calculus has provided for us. So the big picture of least squares, this is exactly the same conversation we've already had, where we talked about the fact that the b vector, which he hasn't drawn in here, I'll just show you where I drew it. So the b vector is right here, like this. And it has the two components. It has the p component over here, and then in red I will draw the error component, which is over here. And when we add the error and the projection together, we end up with our b. So he's just repeating the conversation that we had, and he talks about how we're going to minimize this error term here. Obviously, b minus ax or ax minus b makes no difference when we're talking about the magnitude of that vector squared. It doesn't matter which direction we point in. So fitting the line, this is the conversation specific to the line. And what you'll notice is down here, he comes up with, and let me go a little bit and then I'll go back up for a second. He comes up with this set of equations right here after talking about minimizing the line. But what are these equations? Those are exactly the equations that we just derived using the calculus and setting the partial derivatives equal to 0. So this whole conversation that he has here, you want to read through this, but this is really exactly what we've already been talking about. The graphic over here is again a demonstration for what we are doing when we are minimizing the squared error. So the residuals are in here as the distance between the data and the model, and then we take that squared. Squaring does two things for us. The first thing it does is it gives us the positive values regardless of whether the error is positive or negative, because we don't want to be prejudiced against positive or negative error. Those things don't cancel each other out. They're both error. So by squaring, we make it all positive. The other thing we do is we punish values that are farther and farther away from our model. So because as we move away from the model, the area increases as the square, we end up punishing those data points more than the ones that we're reasonably close to. Let me show you a demonstration of this. So, and I'll turn off the squares for a second. So here is a set of data points, and I have my approximation here. And this square residual shows exactly what we talked about. So the residuals are just the vertical drops, right? The residuals are just the vertical distance between the data and the actual model. And that model, remember, is our best approximation. That is the A times X, or the least square solution. And what we're doing then is we're trying to find something that minimizes this. In this little graphic, and you can look these up online, there are lots of least squares apps. You can play around with these things to help build your intuition. We're trying to minimize this sum. And you can see we have this really large square over here. So if we shift down a little bit, and we can see right in here watching, we can kind of pick out for this particular slope what our best position is. And it looks like it's right in there. But maybe we don't have the right slope. Maybe our slope is too steep and we want to decrease the slope a little bit, and you can see the sum is dropping again. And so now the sum is minimized right about there, and we could shift our line up or down. So instead of playing this game of trying to find out what the best error is, we can just use linear algebra. We can take a look at what the best fit line actually is. You can see that our slope was not correct. We needed to flatten it out even more in order to minimize the error. But this is what the linear algebra is doing. It is finding the red line. It is finding the model, not our guess, which is the blue line, but the actual model which minimizes the error. It just does that for us. And it does that for us because it's solving the calculus problem that we talked about. All right, so that's the conversation about the straight lines. One more topic in here, which is about the orthogonal columns. So it turns out if we had our way, we would always have an A matrix with orthogonal columns. And he highlights in here why that would be true. If we have orthogonal columns, then when we calculate the A transpose A, which remember, we're going to always be solving this set of equations called the normal equations, we're going to calculate A transpose A, and A transpose A would be diagonal. And the beauty, of course, of a diagonal matrix is the inverse is basically free. So in the case where we have a diagonal matrix, we could immediately write down X as A transpose A inverse A transpose B. And these problems would be really easy to solve. Generally, we don't have an A matrix that has orthogonal columns, but we sure wish that we did. He does talk about one approach here about shifting the value. So when we're doing the line, we can shift the values to center them at 0, we can do what's called mean centering, and we can bring the mean of those t values to 0. And that's going to end up giving us, when we only have the 2 columns here, that's going to end up giving us orthogonal columns. Okay, dependent columns of A, this is a niet. If you look in the syllabus, we are not covering this section. The reason we don't cover it is because when we pick a model, we are going to choose a model that does not have linearly dependent terms inside of it. And as a result, our coefficient matrix A will never have linearly dependent columns. So the last discussion here, and this is one for you to read on your own, this is talking about finding the parabola. So again, he uses the not very good notation with his business like this. What I want you to think about is, you're going to think about, I have a quadratic model, which is x0 plus x1t plus x2t squared. And for each data point, we're going to plug that data point in, and we're going to have b sub I is equal to x naught plus x1 t sub I plus x2 t sub I squared. And we'll have m equations for our m data points. And we can easily see how this is going to work out for ax equals b. The A matrix is going to have, and I'll just show you this, we have an x naught, we have an x1, and we have an x2. And what is x naught always multiplied by in each of these equations? Remember, every row is an equation, same as it's been. This is equal to b. X naught is always multiplied times 1. What is x1 multiplied by? It's multiplied by the t values. And then what is x2 multiplied? It's multiplied by the t values squared. T1 squared, T2 squared, T3, however many data points we have, all of those values squared. So we set up the A matrix, and now what we're going to do is apply A transpose via left multiplication to build the normal equations. The normal equation solution is the least square solution, and it will provide for us the best possible model. We will end up with as good of a model as we can come up with. Take a look through the worked examples. He does a really nice job of working through some of the information and some of the examples, and then it's time to shift over and take a look at our questions. All right, so these are the problems that we're going to take a look at. We're just going to rework some of the examples that are in the text. So this is a new set of data for example number 1. And then here's a new set of data for example number 2, where he's using the orthogonality. And then finally, what we want to do is apply this idea of orthogonality, how we can do a shift in the t values in order to solve the original example 1 that Strang provides for us in his text. So those are the problems. Thanks very much, and we'll see you in class.